Hello everyone, Mr. Minix, my name, math is my game, and this morning, 8 o'clock, Mr. Minix is going to be sharing with this first period Algebra 2 group some information about simplifying radicals. Now that we're officially ready to go, earlier there was a typo on the board, and it was pretty funny what it said. So anyway, the kind of thing we're talking about is something like this, the square root of 50 is the first example I wrote up on the board. So if we look at that, you might think to yourself, well, that doesn't look bad, it doesn't look like it needs anything done to it, but it does need something done to it. So the first thing you got to realize is a radical is in simplest radical form, is in simplest, a radical is in simplest radical form, simplest radical form. I've said before about math, it's a lot of times about understanding the language, so there's going to be a lot of words here. A radical is in simplest radical form when the radicand contains no perfect square. Oh man, perfect squares. Again, no perfect square factors. Oh no, the F word again. Larger than 1. Take a minute, break that down, we'll unpack that. A radical is in simplest radical form when the radicand contains no perfect square factors larger than 1. So if we look at the square root of 50, we think about the square root of 50, we would ask ourselves, can we simplify the square root of 50? Because sometimes you don't have to simplify anything with the square root of 50 if we break that down. When we're talking about a radical, this radical 50, that's what we're talking about. Simplest radical form, that means can we simplify it? So we're talking about the radicand, and that's a fancy way of just saying this number. The number under there. Okay, so when we mention the word radicand, we're just talking about the number or the expression or the quantity that's under the square root sign. Okay, you'll hear me, you'll refer to the radicand a lot. So we're talking about the radicand, and we're talking about its factors, so we're going to have to break 50 down into its factors, 1 and 50, 2 and 25. I think there are more factors of 50 than that, aren't there? Is there another pair? 5 and 10, yeah. 5 and 10. So we're saying a radical is in simplest radical form when the radicand contains no perfect square factors larger than 1. So if I'm talking about perfect square factors, the perfect square factors here are 1. And is there another perfect square factor of 50? 25. Okay, so the fact that 50 has a factor 25 means we do have to simplify. Okay, it means that expression is not in simplest radical form. So hopefully you can understand when something can be simplified and when it can't. Does that make sense? All right. I hope everybody remembers how to find factors by number. I know we've been doing that a long time. Okay. So here's the step-by-step algorithm, the procedure for simplifying radicals. Step 1 is find all factors. Find all factors of the radicand. And I might have just lied to you, and I really don't like to lie to you or mislead you. So I'm going to clarify this statement. You don't have to find all the factors of the radicand. But what you do want to find, is the pair that contains the largest perfect square. So maybe I shouldn't even say to find all of them, because really you don't have to find all of them. Sometimes you can stop halfway through. So when you find the factors of the radicand, the pair that contains the largest perfect squares is really what you're looking for. Okay. So once you've done that, the next step in this algorithm I'm going to share with you. And I know some people like algorithms, some people hate them. But this is a really good algorithm, probably the best you'll ever see. I'm not saying that to toot my own horn, just saying this will get you the answer every time. The next thing you want to do is then rewrite the radicand as the product of those factors, as the product of those factors. Okay. So then you're going to rewrite the radicand as the product of those vectors. And some of this might seem a little vague right now. We'll tie this back into the last example. So we're going to find the factors of the radicand. We're looking for the pair that contains the largest perfect square. We rewrite the radicand as a product of those. And when we do this, I need to make some clarification here. What we're going to do, the commutative property of multiplication says you can multiply numbers in any order, right? What we're going to do is we're going to write the perfect square factor. We're going to write the perfect square factor first. Okay, there's a reason we do that. But we're going to put the perfect square factor first. So we're going to come back to this. So maybe now would be a good time to do a split screen. Maybe now would be a good time to do a split screen. So if we tried that on the 50, we've already got 50 factors listed out, 1, 52, and 25, and 5 and 10. So we already kind of did the first step. The second step is to rewrite the radicand as a product of those factors. So if I'm working on the second step here, I'm going to rewrite the square root of 50 as the square root of 2 times 25. But wait a minute, what did I just do wrong? I'm supposed to put the perfect square first. Okay, so I'm supposed to put the 25 first, and there is a reason for that. Okay, so I'll write the square root of 25 times 2. Some of you already know what's coming next. Right? And if you do, I'm sorry if this is boring you to tears, but okay, so the next thing that we got to realize is there's this thing called the product property. The product property. And let me just make this a single page here. Okay, the product property. The product property for radicals is only true for positive numbers. Don't try it on negative numbers, bad things happen. But it says that the square root of AB is the square root of A times the square root of B. Now that's a good definition that can go in either direction, and you'll see later on that it's sometimes effective to use in the opposite direction. But we're going to apply the product property now. So we're going to apply it. So this product property, this is what we're using. And this 3-step or 4-step or however many steps it is, this algorithm, you're going to get to the point you're not going to even have to go step by step. You're going to be able to combine 2 or 3 steps in one. But I do want you to understand the mechanics of it, the math behind what's happening. So what I mean by that product property and applying that is if we look back at the last example, then we can split up this square root of 25 times 2 as the square root of 25 times the square root of 2. Right? The last step then is quite simple. Simplify, get ahead of myself here. Simplify the perfect square. Simplify the perfect square. So we know that the square root of 25 is just a number, right? What is the square root of 25? 5. Good. So then our final answer, this square root of 25 becomes just 5. The square root of 2, there's really nothing to do to it, and it remains as the square root of 2. It is 5 radical 2. That's our answer. Now, I remember when I learned how to divide the first time, I had no idea what happened to the remainder. And I remember when I learned how to simplify radicals the first time, I had no idea where the numbers came from or where they went. And I'm sure that there's many of you in the same position where you might write the answer as something like 2 rad 5, which isn't the same thing. What I'd like to do is I'd like to get out Darth Vader, which is my TI-inspired CAS, and I'd like to show you one thing that it can do that the other calculators can't. Maybe I already showed you this. It's going to take a minute to load. While it's loading, I'll just take a brief moment and give a shout out to my sixth period classes. Thanks for being troopers and watching playback while I'm in the back. Either taking copious notes or grading papers, or sleeping. So does anybody have any questions about this algorithm, this procedure so far? Would you be able to put this procedure in your own words if you had to in an upcoming test or quiz? If I ask you, without simplifying it, explain how to simplify this. Without simplifying it, explain how to simplify this. Could you do that? Explain how to simplify something like the square root of 48 without actually simplifying it. Okay. So this Inspire, I really wish this calculator played better with Windows 10 and the smart software. Maybe I got too many windows open. Maybe I need a new computer. Maybe the computer realizes that it's Monday. Well, while that's loading, I'm going to go ahead and start up another example. So, example, simplify the square root of 42. This is my favorite example on the planet. My favorite example ever. I'm going to try to simplify the square root of 42. So remember the first thing, there's really no getting around finding factors. You want to find factors of 42, so there's 1 in 42. And what I like to do, you don't have to do this, but what I like to do is circle anything that's a perfect square. So there's a perfect square, right? 1. And then we know that 42 is even, so 2 divides it 21 times. And we know that 4 plus 2 is 6, and 6 is divisible by 3. You probably didn't know that 14 and 3 are factors, but they are. 3 and 14 are factors of 42. The other ones you probably knew are 6 and 7, right? So 6 and 7 are the other factors. So I'm taking a good look at that list, and I'm looking for any perfect square, and the only one that's there is 1, right? Anybody know what this means about the square root of 42? It's a state. It's already in simple radical form. There's nothing to do. If you're asked to simplify it, you would just try for your answer the square root of 42. Why is that? Because none of the factors contain perfect squares larger than 1. It's already in simple radical form. Now, lucky for me, I've got this TI Inspire cast that can simplify things. Your yellow Inspires that you use aren't going to do this for you. So if I type in the square root of 42, check this out. Well, I said if I type in the square root of 42. Well, not the square root of the square root of the square root of 42 is square root of 42. If I type in the square root of 50, it's 5 right 2. Okay. How's everybody doing so far? Okay. Good. Wow. Oh man. You know what voice I think I have on this the whole time? I forgot that I had that. That whole intro of the video is going to be in my alien voice. Sorry for the playback. Well, that was interesting. Let's try this now. Example, simplify. Well, since we had those crazy voices, maybe we'll try this one. Let's try this one now. Let's see if we do any better with this. Simplify the square root of 48. The square root of 48. I can't believe I didn't notice that earlier. I'm sorry. Square root of 48. So we got to break down 48 into its factors. 1 and 48. 2 and 24. Let's see. So 1's a perfect square. 2 isn't. 4 goes into it 12 times, and 4 is a perfect square. So maybe I should use those. Should I use 4 and 12, do you think? Let's go back a minute to that algorithm. There is a reason that I underlined twice the bit about the largest perfect square. You see how I underlined that twice? So here's the kind of stuff that freshman students will, the mistakes that freshman students will make. They'll say, okay, so this is the square root of 4 times 12. So this is the square root of 4 times the square root of 12. So this is 2 times the square root of 12. And they'll say that that's their answer. Well, what's wrong with that? Yeah, the 12 can be factored, and 12 has a factor that's a perfect square bigger than 1, doesn't it? So that's why in this algorithm I made it real clear to say you want to look for the pair that contains the largest perfect square. You'll save yourself a lot of headaches, right? So that does require taking a little bit of extra time in realizing that 3 and 16 would be the pairs that you probably wanted in the first place, right? 3 and 16. So I'm going to rewrite square root of 48 as the square root of 3 times 16 or 16 times 3? 16 times 3. And then I can break this apart, right? So it's the square root of 16 times the square root of 3. And we picked 16 for a reason. We know 16 square root is 4, so our answer is 4 times the square root of 3, also read as 4 rad 3. How's everybody feel about that? Are we ready to start jumping to the shortcut? Let's write down a good shortcut. I normally don't endorse shortcuts, but I am going to write one here. The shortcut is this. The square root of the perfect square factor is the coefficient, So when you simplify one of these, the real easy way to look at it is the square root of the perfect square factor. Remember, we're talking about the biggest perfect square factor, but the square root of it is going to be the coefficient. The other factor is the radicand. The other factor is the radicand. The square root of the perfect square factor is the coefficient. The other factor is the radicand. So this is kind of combining steps 2 and 3 and 4. So if we try to simplify something like the square root of 8, after we've found all the factors of 8 that we want, 1's a perfect square, 4's a perfect square, and 2 and 4 is going to be the winning pair. The square root of the perfect square factor. The square root of the perfect square factor. The square root of the perfect square factor, that's this that's the square root of 4, right? What is that? 2. So out of that we have a 2. And the other factor is the radicand. So this other factor here is this 2. So under the radical we're going to have a rad 2. That was probably a bad example to pick because it ended up being 2 rad 2. So let's try this a couple more times. Let's try the square root of 72. This is probably my third favorite example. The reason I like 72 is because it's got lots of factors. Oh man. And it's real nice to show you where to start looking in this list. 1 and 72, 2 and 36, 3 and 24, 4 and 18, 6 and 12, 8 and 9. You know what I should have done is I should have stopped a long time ago. Shouldn't I have? Where should I have stopped? 2 and 36, yeah. I should have put on the brakes right here. So what's my answer on this one going to be? 6 rad 2, nice. So my answer here is going to be 6 rad 2. How do we feel about being able to simplify a radical like that, all right? Any questions, comments, concerns, short or long debates? So, you know what people always ask after you see about 4 or 5 of these and they're real easy? Is it going to get any more difficult? Of course it is. This is Algebra 2. This is varsity math, son, daughter. All right, so rationalizing the denominator. Rationalizing the denominator. Has anybody ever tried to drink orange juice after brushing your teeth? That's the worst, isn't it? And in math, there are certain things that are the worst, like putting a decimal in a fraction, or putting a radical in the denominator. If you had something like 3 divided by the square root of 3, to mathematicians, that's just nails on a chalkboard. That's orange juice after brushing your teeth. That's 20 minutes of a video with the voice on, an alien voice for the first 20 minutes. Maybe it wasn't quite 20, but anyway, you get the point. So the deal is, this is bad. Having that radical in the denominator is bad. Okay, so what we're going to have to do is this trick of multiplying by 1. So I'm going to multiply by 1. But my 1 isn't going to be the actual number 1. It's going to be an equivalent version of number 1. But I need to multiply by something that's going to take that radical and make it go away from the bottom. Now, I don't know if you know this or not, but if you multiply rad 3 by rad 3, so if we're looking at just the bottom here, if we're looking at just the bottom, if I multiply rad 3 by rad 3 in the bottom, what's going to happen is the denominator is going to become, by the product property, rad 3 times 3, isn't it? And so the denominator is going to become rad 9, and so the denominator is going to be just 3. Okay? But I said I got to multiply by 1. So I got to multiply by a rad 3 in the top also. So in the top, I'm going to have a 3 rad 3, a 3 rad 3. I said I'm going to have a 3 rad 3 in the top. And I'm not done with this one just yet. What can happen with the 3 in the top and the 3 in the bottom? They can cancel. They can cancel. So my answer here would just be rad 3. My answer here would just be rad 3. Now, these ones are kind of tough, but there is a shortcut to these, and I'm going to show you the shortcut. And it's awesome because it always works. Sometimes you just have to simplify on the back end. So if we had this fraction 3 over rad 3, there it is, rad 3 is the answer. Okay, so I'm not steering you in the wrong direction. So if we had something like 1 divided by the square root of 2, here's the shortcut way of thinking of it. What's going to happen is the denominator goes to the numerator. The denominator goes to the numerator. And it's going to join anything that's there. It's going to join anything that's there. So I've already got a 1 up there. The whole denominator, that rad 2, is going to go up top. And in the place of the denominator will be just the radicand. Just the radicand. Just the radicand. In other words, no square root sign. Just the radicand remains in the denominator. In the denominator. Okay, just the radicand will remain in the denominator. So in this example with 1 over the square root of 2, we saw the square root of 2 joins the 1 up top. So what's going to be in the bottom? What's going to be in the bottom? Just the radicand. So just a 2. Just a 2. And then finally, we should go ahead and simplify if we can. Simplify if possible, or if necessary, I should say. Simplify if necessary. Is there anything we can simplify? 1 times the square root of 2 over 2, is there anything we can simplify? I see one little thing we can simplify, no pun intended. I see one thing we can simplify. The 1 up top, right? We don't really need to write that. So here our answer is just going to be rad 2 over 2. Here our answer is just going to be rad 2 over 2. Okay. So this is just going to be rad 2 over 2. So let's see, 1 divided by the square root of 2. Really? Now it's going to make it 22. There we go. Rad 2 over 2. All right. Try a couple more of these. What about 3 over the square root of 6? Let's try that one. 3 over the square root of 6. So we said the denominator is going to join the numerator. So that's going to be 3 rad 6 all over what? All over 6. Good. Okay, so we did that part. The denominator joins the numerator. The radicand remains in the denominator. And then we need to simplify if necessary. Is there anything to simplify? Yeah, the 3 and the 6 are going to simplify, right? So the 3 and the 6 are both divisible by 3. So the 3 turns into a 1, the 6 in the bottom turns into a 2. So the whole answer then is going to be what? Rad 6 over 2. How's everybody feeling about this, all right? Let's try another one. Let's try 8 rad 2 over rad 5. Ooh. So remember, the denominator joins the numerator. Already in the numerator is 8 rad 2. So a rad 5 is going to join that up top, right? And then what's going to be in the denominator? Just a 5. Nice, good. Now, I don't know if you can tell this or not, but this rad 2, rad 5, we got to use the product property and squeeze those things together. So according to the product property, what that's going to become, rad 2, rad 5 is going to become rad 2 times 5. So that whole thing's going to become rad 10, isn't it? Okay, so we're going to end up then with 8 rad 10, and that's all over 5. And there's nothing else to simplify here, right? Because 10 doesn't have any perfect square factors. 8 and 5 can't cross cancel. So just to confirm that on my Inspire, I can do 8 rad 2 over 5. 8 rad 2 over 5. 8 rad 2 over rad 5. There we go. Okay. Don't you wish you had the TI Inspire cast for some of these? Okay. So the last thing then, there is this thing called the quotient property that you need to apply sometimes. The quotient property says that if you have the square root of a fraction, it's the square root of the numerator divided by the square root of the denominator. It says that the square root of a fraction is the square root of the numerator divided by the square root of the denominator. Now we actually see this when we simplified, when we completed the square. I think we ran into this a little bit. And you're going to see this a lot with quadratic formula in chapter 5, or completing the square. So what I mean by this is if you had something like the square root of 3/4, that's the square root of 3 over the square root of 4. And that one actually shows up in trigonometry. So up top we'd get the square root of 3, and what would be in the bottom then? Just a 2. Nice, good. That'd be just a 2 in the bottom. Okay. So if we had something like the square root of 9/16, that would be the square root of 9 over the square root of 16. And what would that be? That'd just be 3/4. Good. That would just be 3/4. Okay. So I've got one epic example of this, and it's my favorite of all times. You ready for it? My favorite example of these, the square root of 50 over 10. Maybe I should write it as the square root of 50 over the square root of 10. Yeah, I'll write it like that. The square root of 50 over the square root of 10. So this quotient property does work like the product property in the regard that it's true in both directions. It's not just true in one direction, and yes, I did say one direction. It's not true just in one direction. It's true in both directions. So what I want you to see is we would have to say, okay, so this is the square root of 50 times the square root of 10 over 10, which is the square root of 500 over 10. And the square root of 500 would be 10 rad 5 over 10, and the 10s would cancel, so it's rad 5. But what I could have done right from the beginning is I could have just said, okay, this is the square root of 50 over 10, which is the square root of 5. Do you see where sometimes it pays you to apply the product property or the quotient property before you go doing all kind of simplifying? Anybody have any questions, comments, concerns, short debates, long debates? I said we'd finish a little early, and I didn't lie. I'm actually going to finish a little earlier than I planned on. One final thing is this: the square root of a squared plus b squared. A lot of students in pre-calculus and in calculus and in advanced math classes, they like to make up their own properties. They like to say that this is the square root of a squared plus the square root of b squared. Well, I got news for you. No, it's not. Okay. I don't know if you remember in geometry when you did the distance formula, how you couldn't really simplify it. Same thing. Okay, the square root of a squared plus b squared is just the square root of a squared plus b squared. Okay, you really can't simplify it. There's no rules to say that we can split those apart. Does that make sense? Maybe it does, maybe it doesn't. Just to confirm this, what if we had something like the square root of 8 squared plus 3 squared? Okay, that would be the square root of 64 plus 9, which would be the square root of 73. Now, if you thought that you could break that apart, that'd be the square root of 8 squared plus the square root of 3 squared, so that'd be the square root of 64 plus the square root of 9, so that'd be 8 plus 3, which would be 11. The square root of 73, isn't that going to be like 7 something? Or 8? No, a little bigger than 8, right? So hopefully you realize then that, that this is no good. So that's no good. Okay. Any questions, comments, concerns? Well, that's it. It's been real. It's been fun. I'd like to give a shout out to the future Mr. Minnick. I'd also like to give a shout out to the TC Helicon Perform V for making our day for the first 10 minutes of this. Have a nice day. See you. Good.